Okay, welcome ME311 and 313 students. I've been asked to shoot a relatively brief video, I hope no longer than 20 minutes. I'm going to do my best to keep it well under that. But essentially, what we want to do is cover fatigue and go over a few things that will help make understanding the lab a lot easier for you. So the first thing we want to do is discuss the importance of fatigue and what is it, and then talk about basic test methods and talk about what you're going to be doing in the lab you're running. And then a little bit toward the end of the slides, we'll talk about fracture surfaces and also a very important concept known as the endurance limit. So these are the four things we're after in today's talk. So fatigue failure is essentially the application of cyclic or repeated loading. The classic case is you walk into a conference room or maybe a classroom and there's a little paper clip on the desk, and most people just can't avoid the temptation to unfold the paper clip and bend it back and forth in their hands. And some people can maybe just bend it 2 or 3 times and it fails. That would imply that the stresses or the loads you're applying to the paper clip are very high. Alternatively, someone might unfold the paper clip and kind of just twang it or bend it ever so slightly back and forth in their hands. And maybe you can do that for several minutes or even several hours if the load is very low, but the paper clip will probably eventually fail. So why is it important to understand that? Well, it's probably the second case that I just mentioned that even with relatively low loads or low stresses that are well below yield, well below the ultimate strength, you can still break the part. And that's one of the reasons why fatigue is so critical, because I would say about 50 to 90% of all mechanical failures are tied to fatigue. In other words, if your part doesn't have any cyclic or time-varying loads, it probably won't break ever. You know, look at your dinner table, look at a chair you sit in. In general, it's just sitting there. It doesn't have a lot of moving parts. Whereas a component on your bike or on an airplane or your car has millions, maybe in some cases billions of fatigue cycles, and it's very, very possible to wear out or break the part over time. All right, so we just have to have some discussion of some basic terms and parameters before we move on to the talk, because we're going to be discussing cyclic stresses in a lot of detail and things like mean stress and so on. So here we just want to discuss different load spectrums. So for example, we have these plots of, this is just stress versus time. So in this case, we have, notice the max and the min stresses are equal. And when that's the case, especially when the max stress is the opposite of the min stress, they call this completely reversed loading. And the mean stress is 0. And we'll define the mean stress on the next slide. Now, the other case that's probably a bit more practical is when you don't have the mean stress equal to 0, or you have non-zero mean stresses. And that's, you can see we have, the curve is sort of shifted, if you will, above or below where the origin was, if you will. All right. Now, you can, of course, you can notice we're also applying a loading in a very nice, smooth, you know, I guess you'd say it's like a sine wave. But notice that you can have random loading. You could, a classic case for that might be something like you're an off-road bike rider and you're going down a trail with bumps and hills and jumping over logs and, you know, making really aggressive tight turns. Well, the loading on that is totally random. So you could have, in the lab environment, you're probably testing this top one in many practical applications, maybe the middle case if you can control the loading. But in real life, the random loading is probably what you're going to be exposed to. All right, so let's just define a few more things. So mean stress is basically just the average stress. We take the max stress and the min stress and divide it by 2. The other things we can look at include something called a stress range, which is essentially the delta or the change of the max stress and the min stress. And then there's something called a stress amplitude, which is taking the difference and dividing them by 2. Okay, so just some terminology there. Now, let's talk about the testing you're going to run. And in most cases, we have these tabletop devices, and we have several at Mason, and they're not very big, they're not very heavy, and you can get a lot of data very quickly. And there's different types of arrangements, and we'll look at some pictures in a minute. The most common, perhaps one of the first that was invented, was what they call the pure bend test machine. That just means over the gauge section, there's no transverse shear. It's just purely in a case of bending, hence the term pure bend. The one we have in the lab is called a cantilever bend. So there is a transverse shear component, but it's usually very, very small compared to the more dominant mode of loading, which is the bending moment itself, okay? And in most cases, when you're conducting tests in like a laboratory air environment, the specimens are often cylindrical, and they have usually a very polished, smooth surface, okay? So those are just some things to note as we dig into more details. So this is what the typical, this is the pure bend test. This is very traditional, very classic. And essentially, this is what the specimen looks like. So it has this hourglass shape because we typically want the specimen to break in the middle of the sample, not where it's being gripped. So you install the sample, the loading is applied as shown, and when you have this type of arrangement, again, it's in what they call a pure bend condition. And then there's a motor that's going to be spinning the sample. And if it's an electric motor, you can have motors that run, you know, upwards of 10,000 RPM. You can really pile up some cycles in a few hours, millions of cycles, very quickly. And then it's also important to have something to track the cycles. And these systems are designed such that when the specimen fails, there's usually some sort of switch that's tripped that shuts the test down. You can imagine the problem if the specimen failed and the motor's continuing to turn, then you're counting a lot of cycles that are meaningless. So these systems are usually very carefully designed. There's other different types of arrangements. So we just looked at this one here in B. This is the pure bend arrangement. That was the last slide. But the one you have in the lab is what we call a cantilever bend. And you can kind of see why it's cantilever, because this end of the shaft is sort of fixed to this rotating disc, and the load is applied at the tip or free end, right? And then you could have axial loading, where you're pulling and pushing on the sample, okay? So these are probably the three most common bending test arrangements around. All right, this is a really good video. It's about 12 minutes. We're not going to watch it, but I do want to, not the whole thing, but I do want to look at the first few minutes, usually where the test is starting. Then I might fast forward to where you start to see the cracks. This is an axial fatigue test, and it's a really nice video because it's relatively short and tons of great information here. So in addition to this video, you absolutely should watch this one. Lots of helpful insights. But I want to show you during the test, they have a camera in on tight on the sample, and you can see the surface crack start to form, and then the specimen fails. So let me attempt to show you that.
Inserts one end of the specimen into the right specimen grip. With a union nut, he locks the right end of the specimen. Likewise, he mounts the left end of the specimen into the left specimen grip and tightens the nuts. The preparation is now complete. The material tester then selects the appropriate test parameters on the control computer. He intends to load the first specimen alternately with a tensile force of 7 kilonewtons and a compressive force of 7 kilonewtons. The mean force is 0.
Yeah, that would be the completely reversed loading.
On the start button, and the testing machine begins to stress the specimen periodically.
So this is just pure axial loading.
Our fatigue testing machine is equipped with a mechanical resonance drive.
You can see how quickly it's moving.
The specimen.
All right, so I'm just going to skip up to
via a load cell. Meanwhile, the first specimen has already endured over 300,000 load cycles and still seems to be intact. In reality, however, several cracks have already developed starting from the surface, the so-called fatigue cracks. With each load cycle, they grow a bit further.
And you can see this crack is starting to develop here, and you can see it getting sharper and deeper, and then it finally breaks. And the test is stopped. Okay, so I just wanted to share that with you. That's really nicely done there. Okay. All right, so we're going to get back to where we were, which is to talking about the endurance limit. And okay, so we have something called an SN curve, and it might be best for me to switch to the document camera briefly to show you how this data is collected. So let me do that briefly. So we're going to go to advanced, then go to the second camera. Okay, so we're trying to discuss what is the SN curve now. And this is important because you're going to be collecting and reducing data. So let's say I'm doing my paperclip bend test, and I have number of cycles to failure. So let's say I take my paperclip, and I'm going to apply, I don't know, 1,000 PSI to the paperclip. And maybe that breaks it after, say, 3 cycles. I then do 800 PSI, and it breaks at 100 cycles. And I do, say, 650 PSI, and it breaks at 10,000 cycles. And then I do, so let's say 400 PSI, and you can break this up into really any increment you want. But usually you probably go in some sort of, logical, reducing it by 100 or 50 PSI. And let's say we do 400 PSI and it's 50,000 cycles. Maybe we do 200 PSI and it's 150,000 cycles. So if I were to plot that, what would it look like? So I'm going to have stress on this axis and cycles to failure on this one. It would look something like this, right? At the really high stresses, which is up here, that had a relatively low number of cycles. As I reduce the stress, which is down here, you can see the part lasted a lot longer. So they call this the SN curve. Okay, so some materials like steel, and this is one of the reasons steel was invented. It's one of the reasons that steel is so popular. It turns out for many alloys, such as steel, that there's sort of this magic number, if you will, called an endurance limit or fatigue limit. And it's going to vary depending on the material, of course. But when you get to that stress level, you could have, look at this, it just sort of levels off. This implies that you could cycle the part for infinity. Or at least, many billions or hundreds of billions of cycles, right? And the part never breaks. So that's one way to avoid issues with fatigue loading, is you try to design, below the fatigue limit. So if you design anywhere down in here, right below this stress, the part should essentially last a very, very, very long time. Now that's not all materials. So here you have a plot of another material, and this might be something like aluminum. And why do we mention aluminum? Well, your airplane fuselages are made from aluminum. And what do you notice? There's always sort of this downward trajectory to the curve. This would imply that there's sort of no endurance limit, that even at very low stresses, you could still break the part. It might take a really long time, but it could happen. So here you have just a sample of fatigue data for like titanium. You can see the endurance limit for the steels and the cast iron. Here you have aluminum, which doesn't appear to have an endurance limit. And we have the magnesium and maybe the brass. The brass looks like it might eventually level off as well. So, and these are just for the metals. And you can do this sort of thing for composites and polymers as well. And you might get similar looking plots for those materials too. All right, so we just want to talk about sort of the progression of the damage when it comes to fatigue, because we want to look at maybe both the macro and the microstructural features. So what happens with fatigue loaded parts is at first usually you assume the surface is pristine or in really good shape, including the surface. It's polished or it's got no real big tooling marks or anything like that, no big large scratches or gouges. But over time, what happens is, especially if the part is subjected to bending, we know that for the bending stresses, the largest stresses are on the outermost fiber, so it's no real surprise that that's where cracks start to what they call nucleate or grow. And then the crack will kind of grow it propagates in basically a stable fashion for a little bit, or perhaps a long time, depending on how quickly the cycles are being applied. And then the part just kind of catastrophically or abruptly fails. So those are the three stages: nucleation, propagation, and final fracture. Okay, now, again, depending on the material and the environment and the loading, the nucleation and the propagation stages, these two things can represent like the vast majority of the part life, okay? And it's up for some scientific debate, you know, is it the propagation phase that lasts a long time, or is it that the nucleation phase is the part that lasts the longest? For our discussion, it really doesn't matter. The point is that there's sort of a progressive nature by which this happens, and these are the sort of the steps that are most commonly accepted: nucleation, the crack growing to a prescribed length, and then the part basically can't tolerate a very, very deep, long crack, and it just fails. All right, so when we talk about issues that affect fatigue life, one of the most important, especially as it pertains to testing in the lab, is the condition of the surface. So when we buy these samples, they are machined and produced to have a really high quality surface finish. Or we have you polish the samples using like emery paper in the lab. And it's interesting that if we have groups of students who don't polish the samples and students who do, we should see a difference. So the reason for that is, since the cracks form at the surface, the quality or the condition of the surface is very, very important. So if you have a lot of tooling marks, scratches, gouges, corrosion pits, that can really change the fatigue life. It lowers it often significantly, okay? And here's another one. So we normally take data in air, but what happens if you're testing in a saltwater environment or at high temperature or in a chemical plant, or it might be a mix of high temperature and corrosive agents or corrodants? So you can see we have some steel, and here's the data in air, and you can kind of see that the endurance limit is starting to form here. But what do you notice when it's in salt water? It almost looks like one of those aluminum plots where there's no endurance limit. It looks like it's almost an entirely different material. So the air testing is not the end-all be-all. You could have radically different performance depending on the environment. Now, let's just spend a few minutes discussing the fatigue failure surfaces. So if we take a shaft and we bend it, it has like basically completely reverse cyclic loading. A crack is going to start to nucleate or initiate near the surface and then progress inwardly into the part and then finally fail. And what we see here is, if we take our surface and put it in a very powerful microscope, often you have to use something called a scanning electron microscope. You need really high powered magnification. And we're going to blow up a region near this feature here. That's this little hump or ridge. We start to see these really fine, what look like ridges. We call them striations. And what that is for every load cycle, the crack is jumping forward a tiny, tiny amount, right? So as we keep cycling, the crack is moving into the part very, very slowly. And that's what you're seeing here. Those are these little ridges. And these are, again, this magnification is quite high. This is 3.8 micrometers. Remember, a micrometer is like a millionth of a meter. So this is really, really small. These steps are very, very tiny, okay? So that's what you see at high-powered magnification. What you can also see in many practical cases, and it depends, again, on the loading and the environment and the material, is something called a beach mark. Now, this you don't necessarily need magnification. So this is just a failed surface, failed part, and they're just looking at the failure itself turned on end so you can see it. And you can see something called clamshell marks or beach marks. You can see these nice lines. And these are larger features. And these are often telltale signs of fatigue. Now, depending on the material, and you might test some materials that lend itself to these sorts of marks in the lab. And often, how do they come about? Why do they arise? Well, often in mechanical operations or industrial plant equipment, you have startup and shutdown sequences. So if you are using a big machine and you turn it on and you abruptly lower the load or turn it off and a crack is in there, often the beach mark is associated with that abrupt change in the operational environment or service loads. Okay. All right, so that basically takes care of what I wanted to cover. Try to keep the video as relatively short as possible. So again, I can't recommend it enough. If you want more information, this is a really neat video, especially at the very end where they show large aircrafts being tested and a bike parts being tested in fatigue. So highly instructive. I don't want to necessarily watch this video with you now, but you can watch it on your own. It's a really, really nice video. So I hope you found this lecture to be informative and helpful. And please contact me or your lab instructor if you have any more questions. Thank you.